we have discussed the distributions of random variables. So, when we have a sample space and we are interested in certain characteristics arising out of that experiment, such as we are recording the heights of the individuals, life of a equipment, time taken by a sprinter to complete a 100-meter race, etc. So, these are the examples of random variables. However, many times we may not be interested directly in the same characteristic, but a function of that characteristic. Consider measurements where we are recording the errors in the actual measurement. So, the errors may be negative or positive. However, it may turn out that our losses are dependent upon the absolute value of the error in the recording. That means, in place of the random variable x, we may be interested in x square, modulus of x. Suppose x denotes certain astronomical distances. Now, if the distances are, the numbers are too large, we may be interested in a function of x, say log of x, to make them scale to our level. In a similar way, sometimes we may be interested in x square, we may be interested in say a x plus b or sine of x, etc. Now, it is one thing to consider the characteristics of a function. So, in general, suppose I say g x. So, we may be interested in to look at expectation of g x, expectation of g square x, variance of g x, etc. However, we may be interested in the actual distribution or the full probability distribution of g x also. Now, in order to study the distribution of g x, it is important to firstly ensure that g x is also a random variable. Recall that the definition of a random variable says that random variable is a real valued measurable function defined on the sample space. Therefore, if g is also a measurable function on the real line, then y is equal to g x will also be a random variable. So, we start from this result. Let x be a random variable defined on say omega b p. Let g be a measurable function. So, g is a function from R to R, then g x is also a random variable. So, to look at the proof of this, we must prove that the set of all those points such that g x omega is less than or equal to say y is a measurable set for every real y. Now, this is the set x omega less than or equal to, or you can say x omega belongs to g inverse of minus infinity to y. Now, if g is a measurable function, then g inverse minus infinity to y is a measurable set, and therefore, x omega belonging to that, this is also a measurable set, since x is a random variable. So, since g is a measurable function, the set g inverse of minus infinity to y is measurable set. And since x is a random variable, the set omega such that x omega belongs to g inverse minus infinity to y is also measurable. So, in general we will be considering measurable functions of random variable, so that to ensure that they are also random variable, and then we can study the probability distributions. So, now we have to ensure that a probability distribution can be found. So, given a random variable x with cumulative distribution function say capital F, the distribution of random variable y is equal to g x, where g is measurable, is determined. So, now onwards whenever we are considering a function g x, then g has to be a measurable function. So, let us consider the CDF of y. So, let me use the notation say g y, that is probability of y less than or equal to y. Now, this is equivalent to probability of g x less than or equal to y, which is equivalent to probability of x belonging to the set g inverse minus infinity to y. Now, g inverse minus infinity to y is a measurable set, and the probability distribution of x is well defined, therefore, this probability can be determined. Since g is measurable, g inverse minus infinity to y is a measurable set, and since the distribution of x is well defined, g y is also well defined. So, the basic existence of the probability distribution of a function of random variable is established. Now, let us look at the practical aspect of it, that means how do we determine the distribution of a function of random variable. This is the general approach. So, if we use this CDF approach, that means we express the CDF of a function in terms of the CDF of the in the terms of the CDF of x here. So, let us look at this. So, let us consider a function say y1 is equal to say a x plus b. So, if we are looking at the CDF of y1, so here a is a non-zero constant and b is any real. So, this is probability of y1 less than or equal to say small of y1. Now, this is ax plus b less than or equal to y1. Now, this can be expressed as probability of x less than or equal to y1 minus b by a if a is positive, and it will become probability of x greater than or equal to y1 minus b by a if a is negative. So, notice here that both of these are certain probabilities related to the random variable x. If the CDF of x is well defined, that means the capital F x is known, then both of these probabilities are also known. That means, this is equal to, for example, f of x at y1 minus b by a, and the second term we can write as 1 minus probability of x less than y1 minus b by a, which we can write as x less than or equal to this plus probability of x is equal to y1 minus b by a. So, this is equal to f x at y1 minus b by a if a is positive, and 1 minus f of x y1 minus b by a plus probability of x is equal to y1 minus b by a if a is negative. Therefore, you can see that the CDF of y1 is well determined. Another thing that we can note here is that if x is a continuous random variable, then this probability will be 0. So, we will have only these terms here. Let us take another example. Say y2 is equal to modulus of x. So, if we look at the CDF of y2, now notice here that if y2 is a negative number, then this probability is going to be 0, because modulus of a random variable is always a non-negative quantity. So, this is 0 if y2 is less than 0. Now, if y2 is greater than or equal to 0, then we can express this as probability of minus y2 less than or equal to x less than or equal to y2. So, this is equal to probability of x less than or equal to y2 minus probability of x less than of minus y2, which is nothing but the CDF of x at the point y2 minus the left hand limit of the CDF at minus y2, or we can write it as fx of y2 minus fx at minus y2 plus probability of x is equal to minus y2. So, therefore, the CDF of y2 is expressed as 0 if y2 is less than 0, and it is fx of y2 minus fx of minus y2 plus fx plus probability of x equal to minus y2 if y2 is greater than or equal to 0. Here you can note that if y2 is equal to 0, then this term will vanish and this will reduce to probability of x is equal to 0. Also, if y2, if x is a continuous random variable, then this term will vanish. Let us take, say, y3 is equal to x square. Once again, if I consider f of y3 at, then this is 0 if y3 is less than 0, and it is equal to probability of y3 less than or equal to y3 if y3 is greater than or equal to 0. Now, this quantity becomes probability of minus square root y3 less than or equal to x less than or equal to root of y3. So, that is equal to f of root y3 minus f of minus root y3 minus, that is the left hand limit at this point, which we can express as this plus probability of x is equal to minus root y3. Let us consider, say, function y4 is maximum of x and 0. So, here f of y4, once again you can notice here that this random variable is also non-negative. So, this will be 0 if y4 is negative. If y4 is equal to 0, then this is simply probability of x less than or equal to 0, and if I consider y4 positive, then it is the probability of x less than or equal to y4. So, that will be x less than 0 plus probability x 0 less than or equal to x less than or equal to y4. So, if I combine these terms, then this is equal to 0 if y4 is less than 0, and it is f of y4 if y4 is greater than or equal to 0. You can consider it as truncation of x at 0. So, this approach where we find out the inverse image of the set g x less than or equal to c, that is g inverse of minus infinity to c and then expressing the CDF of the function gx as the in terms of the CDF of x. However, many times the function may be quite complicated and we may not be able to express the inverse image set in a proper way. So, we look at the particular approaches when the random variables are discrete or continuous, and we may consider the special methods. For example, if I have a 1-to-1 function, or if I have a 2-to-1 function, and if the random variable is discrete, then we may express the probability of a point in terms of the inverse images taken by the random variable. If we have a continuous random variable, then in place of probability mass function, I will have a probability density function, and then there is some method. So, let us develop these methods. In case x is a discrete random variable, say the random variable is taking values, say xi is belonging to some set script x, y is equal to gx is a function. So, we consider that for y is equal to yj, g inverse of yj could be x1, x2, x r, say. That means, in general, suppose r inverse images are there. Then probability of y is equal to yj, that will be equal to probability of x is equal to x1 plus probability x equal to x2 plus probability x equal to xr, because what we are doing is we are writing it as probability of gx is equal to yj, that is probability of x is equal to g inverse of yj. Now, what are the values of xi's which lead to gx is equal to yj? So, we look at the set of inverse images and add all the probabilities. So, as an example, consider probability x is equal to, say, minus 2 is equal to 1 by 5, probability x is equal to minus 1 is equal to, say, 1 by 6, probability x equal to 0 is 1 by 5, probability x equal to 1 is, say, 1 by 15, and probability x equal to 2 is, say, 11 by 30. Let us consider, say, y is equal to x square. Now, here x takes values minus 2, minus 1, 0, 1 and 2. So, this y will take values 0, 1 and 4. Now, probability of y is equal to 0. Now, this has only one inverse image, that is probability x equal to 0, that will be 1 by 5. If we are looking at probability y is equal to 1, then there are two inverse images, x equal to minus 1 and x equal to 1. So, the probability is 1 by 6 and 1 by 15 will be added up, we get 7 by 30. In a similar way, probability y is equal to 4. Now, this will be probability of x equal to minus 2 and probability x equal to 2. So, we will add 1 by 5 and 11 by 30, which is leading to 17 by 30. So, the probability distribution of y you can see here is described by probability y is equal to 0, probability y is equal to 1 and probability y is equal to 4. Now, this approach is not directly applicable when we have a, say, mixture random variable, or if the function gx is such that the x may be discrete, but gx may not be discrete, or x could be continuous, but gx may not be continuous. Let us take this case. Suppose x is a uniform random variable on the interval minus 1 to 1, and we consider the function, say, y is equal to maximum of x and 0. Now, you can see here that this distribution, this random variable is not completely discrete nor continuous, because probability of y is equal to 0 is half. This is equivalent to probability x less than or equal to 0, that is equal to half. But if I look at probability y is equal to half etc., then that is 0, because thereafter the random variable is continuous. If x is non-negative, then y becomes a continuous random variable. So, in this case we can use the formula that we developed for the CDF of y4, that is maximum of x0. So, for y4 less than 0 it is 0 and thereafter it is f of y4. So, if we use this, we get probability of y less than or equal to y, it is equal to half for y is equal to 0 and it is equal to half plus y by 2 for 0 less than y less than or equal to 1, and of course, it is 1 for y greater than 1. So, we have then density function here, that is f y is equal to half for 0 less than y less than 1. We have the weight half attached to probability y is equal to 0, and in the interval 0 to 1 we have a density function. So, it is a example of mixed random variable, although the random variable x is a continuous random variable, but the function of that is a mixture random variable. We have certain conditions under which from a continuous random variable the function is also a continuous random variable, and the function, the probability density function of the given function y is equal to g x can be determined using a formula. So, we state it in the following theorem. Let x be a continuous random variable with probability density function say f x. Let y is equal to g x be a differentiable function for all x, and either g prime x is positive for all x or g prime x is negative for all x. Then y is equal to g x is continuous random variable with PDF given by f y is equal to f x g inverse y multiplied by the absolute value of d by dy g inverse y over the range alpha to beta and 0 elsewhere, where alpha is the minimum of the g minus infinity g of plus infinity and beta is the maximum of notice here the conditions. We are taking the function such that the function is differentiable everywhere and either the derivative is strictly positive throughout the range or strictly negative. This ensures that the function is strictly increasing or strictly decreasing. Also, it ensures that the function will be a 1 to 1 function. In that case, there is a direct formula for the determination of the probability density function of y is equal to g x. It is described in terms of the density function of x itself. That is, in place of x we substitute g inverse y, which is uniquely determined under the conditions given here, and we multiply by absolute value of dx by dy, because if y is equal to gx, then x is equal to g inverse y and this term is nothing but dx by dy. So, let us consider the proof of this. So let g prime x to be strictly positive for all x. Then g is strictly increasing, and so it will be a 1-to-1 function, and g inverse will also be strictly increasing, that is d by dy of g inverse y will be positive, and this will be differentiable also. So, if we consider the CDF of y, and another thing is that the range we have to consider. If x is over certain range, suppose from minus infinity to infinity in general, then if g is an increasing function, then the minimum value will be g of minus infinity and the maximum value will be g of plus infinity. If g is a strictly decreasing function, then it will be reversed. So, here the range of y will be from alpha to beta, where alpha and beta are defined like this. So, this is equal to probability of g x less than or equal to y, that is probability of x less than or equal to g inverse y. This is ensured because g is a 1-to-1 function. So, g inverse is a 1-to-1 function. Therefore, the regions g x less than or equal to y and x less than or equal to g inverse y are equivalent. That means, whenever g x less than or equal to y is satisfied, x less than or equal to g inverse y is also satisfied. So, this is nothing but the CDF of x at g inverse y. Therefore, the density function of y will be determined by differentiation of capital Fy. So, we get the probability density function of y is Fy is equal to Fx g inverse y multiplied by dy of g inverse y. Since g inverse y was increasing function, the derivative was positive, therefore, this is equivalent to absolute value of this. Now, in case g prime x is strictly negative, then g is strictly decreasing and g inverse y will also be a strictly decreasing function. That is d by dy of g inverse y will be less than 0. So, when we consider probability of y less than or equal to y, this will be equivalent to x greater than or equal to g inverse y. Since g is a decreasing function, here the event g x less than or equal to y will be equivalent to x greater than or equal to g inverse y. So, which we can write as 1 minus f of g inverse y plus probability of x is equal to g inverse y. Now, this term will be 0 because x is continuous. So, the CDF of y is determined in terms of the CDF of x. So, if you differentiate, we get the PDF of y as minus f x g inverse y into d by dy of g inverse y. Since d by dy of g inverse y is negative, so minus of this is the absolute value. So, this is f x of g inverse y multiplied by d by dy of g inverse y. So, you can see that in both the cases the density function of y is determined as the density function of x at the point x is equal to g inverse y multiplied by the absolute value of dx by dy. So, this theorem is useful when the function g x is a strictly increasing or strictly decreasing function. Let us take an example. Say the random variable x is having the density 0 for x less than or equal to 0, it is equal to half for 0 less than x less than or equal to 1, and it is equal to 1 by 2 x square for 1 less than x less than infinity. And consider the function, say y is equal to 1 by x. So, here g x function is 1 by x. So, g inverse function is also same. If I write this as y, so y is equal to 1 by x, so x will be equal to. So, if I look at this is a strictly decreasing function, g is strictly decreasing and g inverse is also strictly decreasing. So, d by dy of g inverse y is equal to minus 1 by y square. The density function of y then is determined by the density function of x at g inverse y multiplied by the absolute value of the dx by dy term. Now, here it is 0, so it will remain 0. Whenever x is less than or equal to 0, 1 by x is also less than or equal to 0. So, when it is half, this remains half multiplied by 1 by y square. Now, the range 0 less than x less than 1 is translated to y is greater than or equal to 1, and in the third region it is y square by 2 multiplied by 1 by y square. When x is greater than 1, it will reduce to 0 less than y less than 1. So, after simplification, this is equal to 0 for y less than or equal to 0, half for 0 less than y less than 1, 1 by 2 y square for y greater than or equal to 1. Notice here that these fxx and fyy, they resemble. So, for x less than or equal to 0 it is 0, here it is 0, here it is 0 less than x less than or equal to 1, then it is half, and when x is greater than 1 it is 1 by 2 x square. So, that is also satisfied here, except that equality at the end point, but that hardly matters, because if I put y is equal to 1 here, the value is half, and here the value at y is equal to 1 is half, and here also. Actually, at the end points, because it is a continuous random variable, the values will be immaterial. So, basically x and y, x and 1 by x have the same distribution here. So, let us look at another example. Say x follows uniform 0 1, and we define random variable u is equal to x divided by 1 plus x. Now, again you can see here that this is a 1 to 1 function. In fact, if u is equal to x by 1 plus x, then the inverse function x is equal to u by 1 minus u. Let us look at the derivative dx by du, that is equal to one by 1 minus u whole square. So, here the density function of x is 1 for 0 less than u less than 1. So, the density function of u is obtained 1 into 1 by 1 minus u square. What will be the range when this is 0 less than x less than 1? So, when x is 0, this is 0, when x is 1, then this is half. It is a strictly increasing function. So, 0 less than u less than half, and it is 0 elsewhere. many times the function gx may not be a one-to-one function, it may be a many one function. For example, y is equal to x square, y is equal to modulus x. So, in that case we see that the region, that is from R to R, the function's domain and range. So, what we do, we look at the inverse image for a given y, and so if there are two inverse images, then we split the region, that is the domain of x, into two disjoint regions such that both of them match map G from each part of the domain to the full range. For example, you consider y is equal to x square. Now, from minus infinity to infinity, this maps to 0 to infinity. Now, for a given y which is positive, I have two inverse images, minus square root y and plus square root y. So, if I consider two portions of the domain, that is minus infinity to 0 and 0 to infinity, both are mapped by this mapping to 0 to infinity. So, the idea here is that in each domain, each part of the domain, the function will be one to one. That is, if we are considering only one inverse image, say root y or minus of root y, then the function is either increasing or decreasing. We calculate the density in each region separately and add. This gives the density function of the continuous random variable in case the function y is equal to gx is a many valued function. So, let us look at the result here. Let x be a continuous random variable with probability density function, say f(x). Let y is equal to gx be a differentiable function and assume that g prime x is continuous and non-zero at all but a finite number of values of x. Then for every real number y, there exists a positive integer n is equal to, say, ny, and real inverses, say x1y, x2y, xny, such that g of x k y is equal to y and g prime of x k y is not 0 for k equal to 1 to up to ny, or there does not exist any x such that g x is equal to y, g prime x is not 0, in which case we write ny is equal to 0. Then y is a continuous random variable with PDF given by sigma f of x k y g prime x k y inverse k equal to 1 to n. This is if n is greater than 0, n means ny, and it is equal to 0 if n is 0. So, the idea is that we consider n separate regions of the domain such that each region maps to the range of G. Calculate the density in each area and sum over all such areas. That gives the density function of y. So, let us look at application of this. I am skipping the proof of this theorem. Let x follow say uniform distribution on -1 to 1. So, the density function is half for -1 less than or equal to x less than or equal to 1. It is 0. Consider the function say y is equal to modulus x. So, here for a given y we have g1 of y is equal to minus y and g2 y is equal to plus y. So, two inverse images for a given y is there. For y positive, if y is negative, n is equal to 0, that means there is no inverse image. And the derivatives here you can see d by dy of this is equal to -1 and d by dy of this is +1. So, if you take absolute values, then both are 1. So, the density function of y is the density function of x at -y into 1 plus the density function at plus y into 1 for y greater than 0. If you want, we can include equal to 0 also, that does not make any difference, and it is equal to 0 for y less than 0. So, this is half plus half, that is equal to 1. Now, when we say y is greater than or equal to 0, here it will reduce to the region half plus half for -1 to 1. So, it is becoming modulus of x between 0 to 1 and it is equal to 0 for y outside 0 to 1. So, you can see that y follows uniform 0 1. If x is -1 to 1 uniform distribution, then modulus of x is uniform distribution on the interval 0 to 1. Let us consider say x follows normal 0 1 distribution. So, the density function is 1 by root 2 pi e to the power minus x square by 2. Consider the function say y is equal to x square. So, now for a given y which is non-negative, we have two inverse images, that is g1 of y is equal to minus root y and plus root y. So, if I look at the derivatives, that will be minus 1 by 2 root y or plus 1 by 2 root y. So, if I take absolute value, it is reducing to 1 by 2 root y. For y less than 0, there is no inverse image. So, the density function of y is the density function at x is equal to minus root y multiplied by 1 by 2 root y plus the density function at plus root y multiplied by . So, now you see the value will be 1 by root 2 pi e to the power minus y by 2, and in the second term also same terms will be coming, because minus root y and plus root y both will give x square is equal to y. So, the 1 by 2 root y 1 by 2 root y term is coming. So, it will become 2 times 1 by 2 root y, that is equal to 1 by 2 to the power half gamma half e to the power minus y by 2 y to the power 1 by 2 minus 1. This is nothing but a gamma distribution with r is equal to half and lambda is equal to half. So, you can see here the square of a standard normal random variable is a gamma random variable. Now, sometimes it may happen that in place of finite number of inverse images, we have infinite number of inverse images. That may happen in cases such as periodic functions which are trigonometric functions such as sine function or cos function, etc. So, the theorem can be extended here. In place of a finite number of inverses, we have infinite number of inverses. So, we again split the domain into infinite number of distinct regions such that each of them is mapping to the full range of G. Calculate the density in each region by the same formula, that is f x of G inverse y multiplied by the absolute value of d by dy of G inverse y, and add in all the regions. Let us take one example here. Say f x is theta e to the power minus theta x for x greater than 0. That means it is a exponential distribution with parameter theta. Consider y is equal to say sine of x. So, we consider sine inverse y to be principal value. So, we consider two cases because sine lies between minus 1 to 1. So, we consider case 0 to 1 and minus 1 to 0. So, if we take 0 to 1, then probability that sine x is less than or equal to y can be expressed as probability of 0 less than x less than or equal to sine inverse of y, where sine inverse is the principal value, plus probability of 2n minus 1 pi minus sine inverse y less than or equal to x less than or equal to 2n pi plus sine inverse y, n is equal to 1 to infinity. So, this takes care of all the infinite number of distinct regions, each of which map to the region sin x less than or equal to y. So, now this probability using the exponential density function, probability of x lying between 0 to sine inverse y is 1 minus e to the power minus theta sine inverse y plus summation n is equal to 1 to infinity e to the power minus theta 2 n minus 1 pi minus sine inverse y minus e to the power minus theta 2 n pi minus sine inverse y plus sine inverse y. If we look at this series here, e to the power sine inverse y terms can be separated out and the remaining terms become geometric sums and infinite geometric series can be added. So, this is simplified to 1 plus e to the power minus theta pi plus theta sine inverse y minus e to the power minus theta sine inverse y divided by 1 minus e to the power minus 2 pi theta. In a similar way, if y is between minus 1 to 0, we can split the regions and evaluate. So, after carrying out the calculations, the density of y can be obtained after differentiation as theta e to the power minus theta pi 1 minus e to the power minus 2 theta pi inverse 1 minus y square to the power minus 1 by 2 e to the power theta sine inverse y plus e to the power minus theta pi minus theta sine inverse y. this is for minus 1 less than y less than 0, and it is equal to theta 1 minus e to the power minus 2 theta pi inverse 1 minus y square to the power minus 1 by 2 e to the power minus theta sin inverse y plus e to the power minus theta pi plus theta sin inverse y. This is for y between 0 and 1, and of course it is 0 for all other values of y, because y will lie between minus 1 to 1. So, if the transformation y is equal to g x is such that the random variable y is equal to g x is also continuous, then the probability density function of y can be determined in terms of the density function of x. If the function is 1 to 1, there is a direct formula. If there is a many one function, then we have to split the domain into disjoint sets such that each part of the domain maps to the full range, calculate the inverse image in each of them and utilize that to find out the density function of y in each part separately and then sum. There is one important result here which connects all the continuous distributions, which is known as the probability integral transform. This basically says that if x is a continuous random variable with CDF capital F, if we define say u is equal to f of x, then u is distributed on the uniform interval 0 to 1. So, this is known as probability integral transform. The converse of this result is also true, that is, if u is uniform 0 1 and f is an absolutely continuous CDF, then x is equal to f inverse of u has CDF fx, basically f here. Now, this is a very crucial result. First thing is that it connects all the continuous random variables. So, if y1 is a continuous random variable with some CDF f1, y2 is a continuous random variable with some CDF, then there exists a function g such that y2 is equal to say g of y1 and the distribution of y2 will be given by this. So, basically what we can do is that we can consider f1 of y1, that is say u, and then we consider f2 inverse of u, then that will be this. So, basically f2 inverse of f1 y1 is equal to y2. In the modern age of simulations, this result is quite useful. So, in some practical problem we may be interested to generate the values of a random variable which is having say exponential distribution. So, we will use a pseudo random number generator to generate numbers uniformly between 1 to say some n, and then we can consider division by n to make it a uniform random variable between the values of the uniform random variable on the interval 0 to 1. Now, if we are having the exponential distribution, so the CDF of that is known, that is capital F is known. So, we take f inverse of that. So, suppose I consider f x is equal to 1 minus e to the power minus lambda x. So, if y is equal to 1 minus e to the power minus lambda x, the inverse function can be obtained. So, minus lambda x is equal to log of 1 minus y. So, x is equal to minus 1 by lambda log of 1 minus y. So, if y's are the uniform random variables on 0 to 1, then if we consider log of 1 minus y and minus 1 by lambda, then xi's will be exponential distributed random variables with parameter lambda. So, these transformations play extremely important role in the simulation of random variables, because we can use some pseudo random number generator to generate uniformly distributed random values, and now for any other distribution we make use of the transformations. So, especially the probability integral transform is extremely useful in this, and also we have the relationships between various other continuous distributions. So, the discussion on the distribution of the function random variables is quite important in this sense, that to simulate the values of various random variables we make use of these transformations. So, now we will proceed to the jointly distributed random variables in the next lecture.